That's propping and needling. So what's the plan? Well, what I'll cover is what propping and needling actually is, what needs to be considered and when we're looking at propping and needling. We will run through some different types of propping with some examples of our previous designs thrown in for good measure, and then Dave is going to take us through a detailed case study of a project that we worked on in Liverpool. And then finally, we're going to host a live Q&A session at the end as well. So first of all, what is propping and needling? Well, what I'm going to talk about today is the temporary works associated with creating openings in walls. I usually see these schemes in cut and carve demolition projects where the scope of the work is opening up an enclosed area to create an open, airy space, which is a trend for most contemporary office spaces and high-end commercial or even residential buildings. So what we're looking at is how to make an opening in a load-bearing wall. That's what it boils down to. A couple of examples of some typical scopes is shown here. And what we have in is an existing load-bearing wall, be that of any construction, typically masonry or concrete. And the scope is to open up the wall. But we need to understand what this wall is doing in the first place and the loadings it's currently supporting, as this will need to be supported in the temporary term. So why can't we just knock the wall down and whack a beam in? Well, the reason that a beam is going in is usually installed is to support the structure above, and this structure could include a wall, floors, beams, roof, arches, some things like that. The typical loading triangle onto a beam or lintel is shown here. So all loading within that 45-degree load triangle is taken by the lintel or the beam, and then in addition to this, half of any point load or distributed load within that 60-degree zone is carried by the lintel. This could be a window opening or a floor or a roof, for example. An extract from the Structural Engineer's Pocketbook by Fiona Cobb is shown here. This is a fantastic book, by the way. Every engineer should have one, in my opinion. But you can see that all the loading from the floor and the wall in the 45-degree zone is taken fully, and then half of any applied load, not the wall self-weight, is taken too. But this model relies on the floor above arching over the opening, which you can see with those red arrows. The loading from the floor above arches around that opening. Therefore, for larger openings or for openings where there's not enough masonry around the support areas to enable this mechanism shown in the orange circles there, this method does not apply, in which case the full loading above the opening should be taken and not the 45-degree loading type which is shown on that illustration. It's also worth noting that it is because of this arching effect why very small openings for services or ducts, which will not require support usually, that's because they're usually less than half a metre, because over about half a metre or so, some form of support will be necessary. So let's look at the type of things that will need to be considered when we're looking at propping and needling. Importance of site investigation. It's absolutely critical that we know what the structure is and how it's currently behaving so that we can predict what it's going to do when we start opening up and putting needles and props in. And it comes down to GIGO, which is garbage in and garbage out. The idea of the solution, if the idea of the solution is based on rubbish, garbage, then the solution itself is going to be rubbish. Proper site investigation is required, and a little thought and money spent at this stage will make for a much better solution, time in, time out. Lateral stability. Before the wall is removed, the lateral stability of the propping and the wall itself needs to be considered. It's a key one. Support of other structures and not just the wall in question. Don't forget that adjacent floors may well need to be supported to remove the live load from the wall, or if the wall is providing some other support other than vertical, perhaps this needs to be taken into account. The whole sequence of construction and not just the propping. This is very important for a couple of reasons. The first being loading on the temporary works. The system designed needs to be designed for the worst case loadings. Therefore, if the structure will be loaded by plant, material storage, snow, potential vehicle strikes during its design life, and not just at the time of installation, then this needs to be considered at the design stage. The other reason why it's key to look at the whole sequence is to do with load history. This phenomena will include how to put the loading back into the permanent structure once the propping has done its job. It's something that needs to be thought about during that scheme. What the permanent works is and what it looks like. If we plan in advance, it may be that we can incorporate the temporary works into the permanent works to make a slick, efficient and buildable solution. Also, it's key to understand what the permanent works is and what it's trying to achieve to enable the design of a suitable temporary works solution. Are there any services in the wall or nearby? Are any exclusion zones of note? The foundations of the propping. This is important as settlement underneath the prop foundation will lead to unsuitable support of the wall, which is quite key. How will the new permanent works be installed and how and what's the plan? We need to understand, or it needs to be properly planned, of how the system is going to work and what the sequence is there. The loadings that must be considered. Are the loadings all coming from above? So it's just vertical support, or are there any point loadings and are they evenly distributed? Overall stability of the structure. Who is taking responsibility for the overall stability? It may be that a particular design is packaged off just to look at that in particular, just that localized design. But if there's multiple openings being made in the structure, whose responsibility is that, and the interface between them as well? And then finally, ask yourself, is the solution buildable? It's very important that the design from both the permanent works and the temporary works is buildable and suitably mitigates the risk using the ERIC principle of eliminate, reduce, inform and control. Openings in load-bearing structures can go seriously wrong if not carried out correctly, and the overall solution must be safe and the sequence of the construction must be practical. So let's use this example here to explore some of these points. I've illustrated here the current loadings that would be acting on the wall. So we've got potential loading from an arch coming from the right-hand side, vertical loading from a wall above through the wall that's going kind of into the picture, shown in red as well. Then we've got floor loadings from above. You could prop those, but the dead load from that floor is already going into that wall. So if you prop the floor, you're only really taking out any of the live load that's on there. And then the load directly above where we're going to put the lintel or beam is also separated because there's a surface riser duct opening through there as well. So these are the kind of things we need to look through. But now let's go through our list. Site investigation, so we're looking for wall thicknesses, layout of the structure including floor spans and floor to ceiling heights, floor construction. What is the floor made out of, and will it therefore be suitable for point loading from the props when we go to prop, which leads us to back propping. Is it feasible to back prop below? The floor below may well be occupied by a third party, which would mean that we can't back prop. The lateral stability and the support of other structures. We have an arch here. Will that be supported by the needling scheme? Is this wall acting as a shear wall potentially and providing stability to the structure as a whole? The construction sequence and how the new beam will be installed. So what's the permitted working space? Is there a specific construction sequence required due to site constraints? How will the beam be installed? Think about the length of it and how it's going to get in once we've got our props in there. The permanent solution. What is it and what does it look like? Does it consider that temporary works will need to be used to install the beam? And believe me, we've worked on schemes where that has not been considered at design stage. Check for any services. Are there any and are they live and can they be redirected or do they need support? Exclusion zones. Are there any local exclusion zones required? Or can there be some exclusion zones in place during the prop installation, which would mitigate some of the risk associated with propping loads if we remove some of the loads from the structure. Deflection and allowable deflection in the structure. This should be governed by the type of structure and its use, but it's very important as it is often the driving load case for the design. And are we supporting vertical loads only? This links back to the arch, and do we need to provide horizontal support there perhaps? Overall stability of the structure where the openings created. If this wall is acting as a shear wall of some description, then the global stability assessment may be necessary. This should be someone reviewing whether you can turn the whole structure into something resembling Swiss cheese with all the holes in it, and can all those openings be made at once? Other openings nearby and the interface between them. This last point also links to global stability, really. On some schemes, we stipulate that openings are carried out and completed on one floor before you move to the next floor, or certain openings open at one point and not the other. This is just to mitigate some risk against global instability, really. And there are other considerations that will be project specific, but if you plan ahead and get some engineering input on the design at an early stage, then the work should go nicely. So now that we know the kind of things we need to consider, it's time to do a bit of shopping, because it is Black Friday after all. And although there'll be no pushing and shoving here, there's plenty to go around, so don't you worry, folks. There's several different types of propping and needling schemes that we can employ, and sometimes the mix between them is most appropriate, but we're going to look at 7 today, which are most common. So let's take out our printed copy of the Argos catalogue for temporary works, and then let's have a look at some schemes which may well make it onto our list during this Christmas time. So first of all, let's look at some smaller openings that are common in typical domestic applications or domestic type of work. So we're talking a maximum wall thickness of around 230 mil, or a double skin cavity wall with openings up to 2.5 meters or so. The first example here is a no more prop solution, or a temporary lintel. It's a single tool that replaces the need for multiple acros, saving on site prep and time, and it's particularly useful on upper floor work because you haven't got your props coming back down. It's an off-the-shelf product that's great for small applications. However, it does rely on that masonry arching effect, therefore, that we discussed earlier. Therefore, it can't really be used near corners or near any openings. And now for strong boys. So these are acro props with a plate on top, and the similar application as the no more props that we've just mentioned on the previous slide in terms of its use, because the prop head attachment is only good for a safe working load of 350 kJ. Therefore, we're talking kind of small scale stuff here. So the steel plate head attachment is shown here, and that's the strong buoy, and it's cut into the wall as at regular centres and supports the brickwork. An example of this propping is shown, and the row of props closest to the wall has the head attachments, and then the row further away from the wall is supporting the floor above to remove some of the loading from the opening and from some of the live loading. And the propping was then founded on some aluminium beams that spanned over the floor to put the loading back into the load-bearing walls, because the structure in the corridor there wasn't suitable for the loadings applied. And then here we can see this concept illustrated. On the left-hand side is a simple scheme where the props are supported on floors, and to the right is that weak floor alternative, which you can see the photos of in the previous slide. Most often the loadings we get from the strong buoy props are low due to their low capacity. Therefore, propping down to an elevated floor slab is usually acceptable, but there should be a proper load assessment being carried out on that to prove that there is. Understanding the floor spans and construction of the floors is critical, which links back to that good site investigation which I mentioned, and the garbage in, garbage out. The strong buoy system is good as the props are all on one side of the wall, therefore the other side can be used for installing your lintel. And let's have a little breakdown of the sequence of that lintel installation. So first, the propping is installed and fully supporting the wall. That's step one. Then an opening is made to receive the new beam or lintel and its pad stones. This doesn't have to be the whole wall from top to bottom. It can just be a slot just big enough to allow the beam and the pad stone to be installed. And then the beam and the lintel is installed and then dry packed to ensure it's ready to take the load. That's very important, that there's a good contact between the top of the beam that you installed and the soffit of the wall that it's taking loading from. That's essential because when you take the wall away from the bottom, we don't want any movement from onto the beam as the wall sags onto the beam and loads the beam essentially. So it's important that we dry pack to make sure it can take the load. Once that beam is taking the load, this temporary support can be removed and then the wall fully demolished to create that full opening. And that's the process in a nutshell, really. So let's look at some larger loadings. This could be a thicker wall, a higher floor load, or something similar. This concept of needling, we've got needles, which are typically steel beams at regular centers, and these are propped down with larger props. We've got nominal fixings between the headers and the props to make sure that we've got a positive connection between all the components of the design. We've also got scaffold tube bracing in the longitudinal and the lateral direction to make sure that when we pick up this wall, that system is stable and is able to support the wall whilst we construct the beam underneath, and then we can take the props away. An alternative to having a needle on top of every prop, or a prop under every needle, the alternative is to use a header beam between the props to support the needles. The centers of the needles remain the same, but what you have is a larger opening between props, which can be helpful for construction. So here we've got 4 props in total, and then we've got header beams on top of those, and then the needles are being posted through the wall and are sat on that header beam. We've got scaffold bracing in the longitudinal direction, but in the lateral direction, because there was an existing wall there, which was what we were taking down, we couldn't have any scaffold cross bracing, so we had a raking prop on one side. That raking prop on one side was suitable because we had a good positive connection between the props, the header beams, and the props the other side, so we were satisfied that the whole system was stable. If we're propping an opening on a raised floor and the floors are weak, then or unsuitable to take the kind of loading that we're getting from the props, then a reverse needling system, as shown, can be used. This scheme takes the load from the wall, distributes it out into the needles, into the props, back into the lower needles, and then back into the wall, just like that is shown. This is a great idea as the load path remains unchanged from the floor above to the floor below, which mitigates the risk associated with mucking about with the load path of the structure. The propping from the floor to the ceiling, that's shown, that's outside the kind of needle props. They're used so that the propping has got something to brace back to for lateral stability. A tall prop such as this is not required on every prop. Here we've got just 1 per 3. It's just there so we can brace back to something and make sure we maintain that lateral stability. If we've got a structure which has got very tall ceilings and a prop such as this, a tall prop such as that is unsuitable, then we can use scaffold raking props or something similar to provide that lateral support instead. And then now as a quick break or an advert in our hypothetical Argos magazine that we're browsing through happily, we can see some bad practice of acro propping and needling. So this is a project we had no involvement in until we got called out, once it was identified that things weren't going too well. This was a domestic builder who was way out of their depth. The wall is basically falling down here, and the floor above is unsupported in places. There's no bracing to the props, and there's no positive connection between the prop heads and the lintel. What we usually recommend is that there's a U head or something similar when you're using acro props, so that you can make sure that the prop head remains attached to the header, so it can't be knocked out accidentally. There's no such thing here, and it's also dubious of how much the lintels that have been installed, dubious of how much bearing that the wall has got onto those. Also, the foundation of this propping was on a raised floor, and so they clearly thought, well, we might need to put some timbers down to strengthen it, but this certainly is not good practice. So the timber should be concentrated in the zone where the props are loading, which is shown there. And then if there's enough timber to double stack, that would go a long way to provide some additional support or additional load spread to further across the floor. But after looking at this, it's questionable if some of these props are loaded at all. But that's some bad practice and things certainly to be avoided. So now let's look at some needling with larger beams and a pinned wall. This is a scheme where the loads were very high as we were supporting the whole facade of the structure. The area beneath the propping was also required to remain open to enable the demolition works and some follow-on construction works. Therefore, we developed a scheme that had props 5 meters apart, which you can see there in blue, large needles at 2.5 meter centers, and then PFCs, which are parallel flange channels, so C-shaped channels spanning between the needles to pick up the wall. You can see that here. So the PFCs are essentially strengthening the bottom line of the wall, and they're also designed to span between the larger needles. A sleeved rod through the wall ties the back-to-back PFCs together, and that essentially allows you to span the 2.5 meters as opposed to like 500 to 800 mil centers of the needles, which you would typically have on a scheme. Here's a close-up of those needles and the pins. It's important that the sleeve is used for a thick wall like this, because the rods themselves, which are just like threaded rods, they've got a very low capacity in bending, and it wasn't suitable for high load and a thick wall such as this. Due to the size of loadings and the awkward site constraints, it was necessary to go with a bespoke fabricated steel solution on this scheme, but you could achieve similar solutions with proprietary, although the back-to-back channel along the wall would have to be a fabricated solution. Another solution which is similar to this is to use just the pinned back-to-back PFC back to some propping. And this is helpful when you've got a wall which may well be heritage or protected, and they don't want to put big holes in for the needles. Then by using this back-to-back PFC, you've got a number of holes, but they're at regular centers and that they're much smaller. So it may be that that could be a solution for your next project. The Pinyford stool method. This is a method of casting an in-situ beam into a wall over a proposed opening. The illustration shown here has been taken straight from the Temporary Works Toolkit Part 10, which is a series of articles that are aimed at assisting the permanent works designer with temporary works issues. It's a great document. I'll come to that a bit later. But the sequence is to break out some pockets in the wall and insert some stools, which are usually steel stools. Once the stools are in and dry packed, i.e. ready to take the load, because the support is very tight to the wall below, then the channel for the lintel can be formed. Into this slot, this horizontal slot which has gone throughout the wall, for the new lintel to be placed, that's made, and then the rebar is placed into that void, ready for the new lintel. Shutters are placed around the slots, and then the concrete is cast. The top of the beam must be dry packed to the soffit to ensure that it's bearing against the top of the wall and there are no air pockets at the top, which could have been formed during the concrete casting process. And then once the concrete is cured sufficiently, the wall then can be broken out, and hey presto, you've got your opening beneath your wall. Here's an example of a design where we've used this Pinyford stool method during a low-cost project in East London. We used steel stools that were designed to sit inside the new lintel and then not clash with the reinforced concrete beam reinforcement. And the process was, as before, make the pockets in the wall, install the stools, form the slot, insert the rebar, cast the concrete, let the concrete cure, and then make the opening. And here's a detailed view of the stool interface with the reinforcement. This Pinyford stool method really is quite handy on certain projects, and certainly is one to keep in mind. In a similar vein to the Pinyford stools, we can use back-to-back PFC stools, so those C-shaped stack channels we mentioned earlier, that allow the installation of some precast lintels, which are very common on smaller openings. The channels are the perfect shape to enable the installation, and the wall is removed once all the lintels is installed and ready to take the load. And we've got a typical opening here that you can see the load interaction zone and the proposed location of the stools shown in the 3 hatch blocks. So those load interaction zones were what we discussed earlier when we were looking at the kind of loading. So we can see that the floor is definitely within that 45 zone, so we're going to be taking some floor loadings and the wall above. So if we take a section through this, then we can look at the sequence of installation. This sequence is similar to the Pinyford stool method. However, as this sequence allows multiple lintels to be installed side by side, which is often the case on thicker walls, one side is usually completed before the other to ensure that the wall receives as much support possible throughout the works. So here's what we do. So we break out the pockets and install the stools on one side only. So you only break out half and install half of the thickness of the wall and install the stools, and then dry pack those stools. Form a slot in one side and then install the lintel. Dry pack the installed lintel, and then this lintel is now ready to support one side of the wall. This process is then repeated on the other side. So you break out the pockets, install the stools, dry pack the stools, and form a slot on one side and install the other lintel. Once both lintels are in and ready to take support, ready to support the wall and take load, this is the point where a temporary works coordinator or usually signs off the installation and permits that the wall below can therefore be removed. And that's that design in a nutshell. It's very helpful and removes the requirement for any propping, because the load path remains within the wall until the lintels take the load, and then that's the permanent works loading. So that's the loading it's going to have in the permanent case. And now I'm going to hand you over to Dave, who's going to cover scissor propping during our detailed case study in Liverpool. So take it away, Dave.
Thank you, Josh. So yeah, what we're going to have a look at here is a fairly interesting propping scheme that me and Josh carried out a few years back now on the India buildings in Liverpool. So a bit of an overview. The India buildings are constructed in the 1930s. It's a fairly old structure with two large light wells. It's kind of got two levels of basement, and then it is a steel structure on top with load-bearing masonry walls in between the steel columns. Our brief was that we were creating a new lift shaft in the building and wanted an opening into that lift shaft. Because the lift shaft was being installed and the steelwork was being installed for that, it resulted in us only having access to one side of the wall to carry out our propping and the lintel installation, and that led to some complications, as well as the different height walls on either side, or different height floors on either side of the wall. So if Josh just moves on a wee bit, you can just see the India buildings there now. And we had some quite good historical information, which is shown just here on the existing structure and the floor heights. So it was a nice little project to work on. So if we move on to the next slide, we can have a look at the concept that we came up with and then the finished solution. So the concept was to needle through at the top and then return the load back into the wall beneath. We used kind of a scissor method here, where we were kind of had a compression strut quite close to the wall to take the load, with a tension strut further out to kind of stop the whole thing closing in on itself. During the works, we had kind of a number of issues with kind of clashes with both existing steelwork within the wall and with the lift shaft steelwork from in the wall behind. And that kind of led us to the solution that we've come up with there. They also found an existing opening when they were carrying out the works, which led one of the needles to being a bit longer. But the solution we came up was using some proprietary equipment. I'm not going to mention who, but I'm sure we can all guess. And that was the solution. We had to allow for a 1 meter gap in the middle to allow for the installation of a beam. So they were using a genie lift to get that in, and that kind of obviously we had quite good conversations with the contractor involved to make sure that the installation could be carried out. And that was the other reason why we had to leave a kind of a reasonable gap between the prop and the wall. So it was slightly less efficient, but it enabled the installation of the new lintels. And the final, we've just got some pictures of the work. So the first picture shows where they've been creating the openings prior to installing it. And you can see the lift shaft steelwork in the back there. That was what prevented us from using a kind of a more standard needling solution. You can kind of see the concrete beam in the middle there, which was the existing floor level on the other side of the opening. prior to the lift shaft installation, and then the openings for the needles. And the picture on the right shows the finalised design prior to the lintel installation, just before they broke out the wall. So it was an interesting project, posed quite a lot of issues to us going into it, but we came up with a solution the contractor was happy with and enabled the works to go ahead. And yeah, it is a very short case study. So I think now we are going to be moving on to questions and answers.
Yeah, so just before we dive into that, thank you very much, Dave. If you want to know any more, there's a host of information out there that covers this subject. There's a whole chapter on propping and needling in the Temporary Works Principles of Design and Construction, which is shown in that yellow banded ICE publication there. It's a great read. And some other examples, there's the BRE Good Building Guides, there's information on Syria, Temporary Works Forum, which has got lots of juicy information on propping and temporary works in general. And then there's a Syria guide for the retention of masonry facades, which helps with deflection criteria. And some, if your opening is going to be something quite bigger, like the one with the PFC sandwiched between the walls, that was more of a facade, really, retention, really. So that's if you're going a bit bigger. The Temporary Works Toolkits, part 10 covers the propping and needling. That's a great document and just covers the nuts and bolts of temporary works associated with propping and needling. So that's definitely worth a read. And that will then lead us on to question time. So it's time for a short